Okay, so picking up where we left off in the last video, this kind of gets us to the point of why we are interested in the big O and the theta notation. Why we're interested in the big O and the omega notation, because if we can find that a function is big O of g and also omega of g, if we have both of those, then we get to write that the function is theta of that same function g. And so the idea is kind of this. Now this is, if you've taken any calculus, you've seen this type of idea. You don't have to have calculus to understand this, but the same type of idea is used in calculus. If you've got a function that's bounded above, and also bounded below by the same function, by that same function, then the conclusion is that what you're really saying is that this function g kind of behaves in the same way, or I'm sorry, this function f kind of behaves in the same way as this function g. I mean, if you got a, right, so here's your function f, right? And you're saying now this is just generally the idea. I've gone through these ideas kind of quickly, and I've kind of paraphrased them, but generally this is the idea, right? So you're bounded above by this function g of x, and you're bounded below by this function g of x. Well, then you can see that the behavior of f is kind of forced to be in between those two. But remember, we found this guy and this guy to be the same function, so kind of those two red functions squeeze together, and they really tell us a lot about how this function f is behaving. In fact, they really behave very much the same way, right? And so that's the point, is that if we can get the big O and the omega to be of this same function g, then we know a lot about how that function f is behaving. Okay, so let me take another function and we'll kind of work through one start to finish now. So what we want to do is we want to find the theta notation. Right, so if we're going to find the theta notation, we first have to find the big O notation and then the omega notation, and then we can conclude what our theta notation is. Now I want to make this look like a polynomial, so I'm going to FOIL this guy out. So I'd have n cubed plus 3n, first outside, inside last, plus 3. Right, so just putting these in descending order. Okay, now I can kind of mimic the two examples that we had above. I can take this function and say it's got to be less than or equal. So I'm just going to multiply. I want to make all of these be n cubed terms, kind of like in my first example I made them all n squared. But so if I multiply here by n, I made this term bigger. If I multiply here by n squared, I made that term bigger. Right, got to be on the greater than side. If I multiply by n cubed, I made the term bigger. Right? Inequalities don't work like equations. I can multiply over here by something as long as I'm sure that it makes this side greater than or equal to this side. Right? That's kind of an awkward idea. We're used to equations, right? But working with inequalities gives you a little more flexibility. Right, so I've made this side bigger because I multiplied by larger values of n, or n squared, or n cubed. right? And then now, so I've made these all like terms, so I've got 1, 2, 3, 4, 5, 6, 7, 8 n cubed, and this tells me that my function t of n is big O of n cubed, bounded above. Okay, similarly to that first example, we can write that since all these terms are positive, 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 if I was just to get rid of those, then what I would have done is made this side smaller, right? So my constant up here was 8. My constant down here is just 1. That tells me that my function is omega of n cubed. And if I have big O and omega, then that tells me my function is theta. Right, and so that's our theta notation. The function behaves like n cubed. And you might have noticed that my first example ended up being theta of n squared, and it was a quadratic function to begin with, right? Because we showed that it was big O and omega of n squared. And then this guy was a cubic, n cubed, and it ended up being theta of n cubed. And that pattern always works for polynomials, right? So whatever your degree is, that's going to clue you into the theta notation, but this is how you would show your work to get to the theta notation. Okay, so maybe one more example, finding the theta notation. Let's take this function, and this is going to provide a little bit more of a challenge for us. And then what we'll do in the next video is we'll see exactly where this theta notation can help us in analyzing an algorithm. Okay, so let's see if we can play around with this guy. Okay, so in getting the big O notation, I've got to put something over here that's greater than or equal to what's over here. Now I've got a rational expression, which ultimately is just a fraction. Right? Now let's think about, we have some fraction. We can make that fraction larger if we do a couple of things. If I make the value of the, well, let's do this instead. If I was to change the value of the numerator, that makes the fraction larger. Alternatively, I could change the value of the denominator. I'd have to make the denominator smaller. 4/3 is larger, right? If I divide by a smaller number, that makes the overall value of the fraction larger. So I'm going to combine these two thoughts. I'm going to make the numerator larger. I multiplied by n, that makes the numerator larger. And I'm going to make the denominator smaller. I'm going to knock off that plus 2. Those are both legal. In this example and this example, you can see making the numerator larger or the denominator smaller makes the overall fraction larger. And so what happens here, oh, I'm sorry, I'm going to make this one even 1 larger. 3n works, but I want these two to be the same, so I'm going to make that 3n squared. Great. And then what's this? This is 4n squared over n, and that reduces to 4n. Right, so here's my constant times my function n. So what I've shown is that my function is big O of n. Okay, so let's see if we can go the other way. So this time I've got to make the fraction smaller. So what if I, okay, so forget these ideas. How could I make my fraction smaller? I could decrease the value of the numerator. That would make the fraction smaller. Or I could increase the value of the denominator. What if I make the denominator some really large number? 4 divided by 100, that's a lot smaller. Whoops, not equals. Not equals. 4 divided by 100 is a lot smaller because I divided by a much larger number. I can either decrease the value of the numerator or increase the value of the denominator. Let's see if we can apply both of those ideas. I'm going to decrease the value of the numerator by getting rid of that plus 3. And I'm going to increase the value of the denominator. So I'm going to multiply this guy by n. Now, I could have multiplied by n squared. That would have been fine. That would have increased the value of the denominator. But I want these two terms to match. Right? I want these two terms to match. And so I'm going to leave that at n, and also in thinking ahead, I want my function g of n over here to be the same. Right? If I made these both n squared, I'm not going to end up with n. Right? If I made this n squared and this n squared, I could do that, but then I'd have n squared over 3n squared, and I would have completely gotten rid of those, and I'd be left with 1/3. Right? But I want to end up with some constant times n, just like I did in the first one. Right? So I'm going to leave this guy as n, because then what that gives me is n squared over 3n. N squared over 3n, and I can cancel an n. Right, so that gives me n over 3, or equivalently 1/3 n. So there I've got my constant times n, right, which is less than the original expression. And so this tells me that t of n is omega of n, and therefore t of n is theta of n. If you get the big O and the omega, then you've got theta. Okay, so those are the basics on our theta notation. And now, of course, we want to take this and do a little bit of analyzing of some algorithms. And that's what we'll do next.